So this is section 5.2, and this is on integration of the natural log function. So in 5.1, we talked about the differentiation rule, and we talked specifically about the derivative of the natural log being 1 over x. So it stands to reason that if the derivative of the natural log is 1 over x, then the integral of 1 over x must be the natural log. Now, remember, we do have that restriction that the argument of that natural log has to be positive, because we cannot take the natural log of 0 or a negative number. So that's where these absolute value bars come in, and those are pretty important. So we say that the integral of 1 over x is the natural log. Now remember, that came because, as a reverse of the derivative of this being 1 over x. So now we have this integration. The absolute value is just to maintain that positiveness, yeah, that's a word, we'll pretend that's a word, of that argument of that natural log function. And then of course we get our plus c. We can extend this, if we need to use some substitution, we certainly can. If u is some function of x, we can extend that. So let's dive right into some of these integrals. So I will try to refresh your memory on integration, because I know it might have been a hot minute since you've done any of these. So if we're looking at the integral of 2 over x, the 2 can be looked at as just, a normal coefficient, and then we know with derivatives, those coefficients are just along for the ride. Same thing with integration. So what I can do is pull this 2 out right here, and then I just have the integral of 1 over x dx. Well, by definition up there, that's just going to be the natural log of the absolute value of x. Yeah, those absolute value bars are important. Oh. Now we know from one of the log properties that this 2 right here, that this coefficient can be written up here as an exponent. All right? So if I do that, then I get the natural log of x squared. Notice I dropped the absolute value bars though. I did that because x squared is always positive anyway. We know that anything squared is always going to be positive. So I don't need the absolute value bars anymore. All right, so let's look at another one. I'm not doing a good job of hiding this, man. This one we're going to need some substitution, okay? Is that kind of blurry? That kind of looks blurry to me. It could just be my bad vision, but we'll see. So this one we're going to need some substitution, okay? We're going to let u be this denominator. And I did that because I saw that the derivative of that was going to be 8x dx. So I looked at that and said, hey, you know what? The derivative of that's going to be that numerator. So that's just a pretty easy substitution, right? We know that those substitutions can get really messy, but this one's actually pretty easy. It's just a 1 over u du substitution. So it's just going to be the natural log of the absolute value of u plus c. And then don't forget to plug u back in. So if I plug in 4x squared minus 5 for u, I do have to leave those absolute value bars on this time. All right? Last time I could drop them off because I know that x squared is always positive, right? But here I'm not guaranteed that this will always be positive. Like for instance, if x is 1, that's 4 minus 5. That's a negative number. So I need those absolute value bars in there. So I was just glancing up right here, and I noticed that I kind of wrote this in my own little language here. This means that x squared is positive for all values of x, so no absolute value bars are needed. So that upside down A is a symbol meaning for all. Man, by the time you guys get out of this class, you are going to know so many different symbols. It's going to be great. All right, next up, the integral of tangent. Seemingly innocent little integral, doesn't seem like a big deal, but if you look at it like in an integral table in your book, you're like, ooh, that escalated quickly. Well, that's because we have to rewrite this tangent as sine over cosine and then use a substitution. So I'm going to rewrite it as sine over cosine. I'm going to let u be cosine, and then the derivative of cosine is negative sine. Now this -1 right here, that coefficient, I can divide both sides by that -1 so that I just replace this sine x dx all with negative du. So this substitution becomes 1 over u and then negative du. I'm pausing to make sure that makes sense. And then this -1 is just a normal coefficient, it's just along for the ride here. And then we know the integral of 1 over u du is just natural log absolute value of u plus c. And then I'm just going to substitute u back in. So I'm going to put that cosine back in. And I get negative ln, absolute value of cosine x plus c. It's not as pretty as you might think. You might think, oh, integral of tangent's probably not a big deal. It's probably something like cotangent or something. But no, it's pretty messy. All right, let's do a definite integral. So we've done a bunch of indefinite integrals, so let's do a definite integral. We are going to need a substitution for this one. All right. You can kind of see that if I split this apart, I'm going to have like a 1 over x, and then I'm going to have a 1 over ln x. So you might be thinking, the derivative of natural log x is 1 over x. And you would be thinking correctly. So I get this u equals ln x, and then du is 1 over x dx. So then this integral is going to become 1 over u du. Now notice, this is my own personal preference here. I don't put my bounds on here. Some people at this point will change the bounds to match this new variable. You know, they'll say, oh, well, when x is equal to 2, u is ln 2, when x is 4, u is ln 4, and just change these bounds to ln 2 to ln 4. I don't particularly like doing that, but I will if that's what you guys really like. But yeah, that's not really my jam. I'd prefer just to leave this, integrate it, so I get ln absolute value of u, and then just plug u back in. So I'm just going to substitute back in for u and put this ln x back in there and then use the original bounds. So it does require you to remember to substitute back in and then use those original bounds, that you don't accidentally evaluate this u from 2 to 4, because those are the bounds for x. So in doing that, we know we're going to plug in 4 and then minus plug in 2. So we get this expression. Now this one's just fine. There is a ton of ln's and absolute value bars, and it just looks like a straight line fiasco here. But here's the really crazy part. If you were to look in like Calc Chat or in the back of the book, this thing right here, believe it or not, will simplify to just be ln 2. So if you get this answer and you look in the back of the book and you're like, oh, it says ln 2, you probably assume, okay, I have done this wrong. I have made a terrible mistake, but you haven't. This just cleans up more. There's just a little bit more simplifying using log properties. So for instance, we know that this is subtracting 2 logs, so I can pull that together into 1 log of division of this stuff over this stuff. Now, 4 can be written as 2 squared, and I'll show you why I did that. Because then I can take this 2 right here, move it out in front as a coefficient, get 2 ln 2. My ln 2's can just cancel there, and I just get natural log of the only thing left inside those absolute value bars is just 2. So it's crazy how these logs can clean up so quickly and easily. And it's, yeah, it's very deceiving because you might get an answer and think that you're wrong. So no matter how nasty your answer is, it could still be right. All right, let's move on along here. Hope I'm not moving too quickly, but at least since it's a video, you guys have the option to pause it at any point. All right, another definite integral. again, with the substitution, we're going to use u being this denominator here. And I hope you can kind of look at this and kind of feel what's going to happen, that you're just like, oh yeah, I can sense it, right? Because the derivative of theta is just going to be 1, then that derivative sine is going to be cosine. So while this looks like it's kind of menacing, it really is not a bad substitution. So if I let u be the denominator, my du happens to be exactly the numerator. So I just get the integral of 1 over u. That integral is just natural log of absolute value of u. I'm going to substitute this theta minus sine theta in for u, and then evaluate it from 1 to 2. So I'm going to plug in 2 for both of these thetas, and then subtract and plug in 1 for both of those thetas. Because that's 2 logs being subtracted, I can pull that together with division. So I just did that little extra step there. And you'll notice that I did leave those absolute value bars in there. Just to be safe, it's probably just safest to just leave them in there. But just know that if they ever get dropped, it's just because that argument's guaranteed to be positive. Okay. So this one's an indefinite integral. And this one's going to be a little bit different. We're going to have to let u be, well, what? If I let u be x plus 1, then the derivative of that is just going to be 1. So I don't really have anything to do with this x up here. So that's kind of messy. That's not a good approach. All right, so maybe if we multiply this out and we get like x squared plus 2x plus 1. Well, that's going to give me a derivative of 2x plus 1, which is more than I actually need up here. So that's not going to work. So what we need with this is a little bit different technique. You've probably seen this before. It's not a super popular technique, but it is something that you need to be aware of. It's called a change of variables. You may think that's what substitution is, but this one specifically, if I let u be this x plus 1, then the derivative of u is dx. We still end up with this problematic 2x up top. Well, here's what we can do with it. If u is x plus 1, I can solve this for x by just subtracting 1 from both sides. And I get a similar equation here of u minus 1 equals x. So I'm going to make 3 substitutions. I'm going to replace x plus 1 here with u. I'm going to replace dx with du. And I'm going to replace this x right here, the 2 is just going to stay. I'm going to replace that x with this u minus 1. All right, so again, the squared is going to stay put. I'm going to integrate that. But I replaced x plus 1 with u. I replaced dx with du. And I replaced this x right here with u minus 1. I just took this equation right here, subtracted 1 from both sides. That way everything's in terms of u, because you know we have to have just one single variable. Now I can distribute this 2 and get 2u minus 2. So I went ahead and distributed that and went ahead and just split it up into 2 fractions. The reason for that is because I knew it was going to be easier to integrate this as separate terms. So I get 2u over u squared minus 2 over u squared. This u cancels one of these, so I just get that 2, which can come out of the integral. And then I get 1 over u here, minus this 2 can come out of the integral. And I get 1 over u squared for this term over here. Now, 1 over u, we know how to integrate that. We've already done a whole bunch of those. That's just natural log of absolute value of u. This 1 over u squared is the power rule. Remember, because this is just u to the -2, so we can just use our normal power rule for that sucker. So we get this 2 right here. That's just a log for the ride. The integral of 1 over u is the natural log of the absolute value of u, minus 2. The power rule here for u to the -2, we know we add 1 and then put it over that number. So -2 plus 1 is -1 over -1, and then plus c. And that just cleans up a little bit here, and substituting back in for u. So that negative divided by that negative becomes a positive. U was x plus 1, so I put x plus 1 back in right here for u. Now, how did this x plus 1 right here suddenly move to the denominator? The u was up here. Well, because it was a -1, I just went ahead and just moved it down to the denominator to make it a positive 1 power. You could have left it up top and had x plus 1 to the -1 power. That's just not usually how we would write things. We usually don't like writing negative exponents in answers. All right. This is one where we're going to want to use the log properties before we integrate. All right. Now, remember, the natural log and e to something are inverse functions, so they undo each other. So this right here just simplifies to just be x plus this stuff right here is just -x. The natural log and the e undo each other. So this is nothing more than the integral of x plus -x. Well, what do you get if you add those together? Those are like terms, so you can add them. That's just 0. What's the integral of 0? Well, the integral of 0 is just going to be 0 plus c, or just c, because we know that the derivative of a constant is 0. So the integral of 0 is just a constant. Alrighty. So with this one, and I'm trying to do a whole bunch of a whole variety of problems so that when you encounter different integrals, you have a bunch of different techniques. So if it seems like, wow, she's not doing the same thing twice, I'm just trying to give you a whole bag of techniques so that when you see one, you can say, okay, I'm going to try this, then I'm going to try this, I'm going to try this, and see what works. So for this one, I would split this up into 2 fractions. I would split this into p over p and 1 over p. Because when you do that, this p over p is the same thing as 1. So now I just have these 2 separate integrals are both really nice, right? The integral of 1 with respect to p is just p. The integral of 1 over p dp is natural log, absolute value p, and then a plus c in there. So this could be one where you might try to use a substitution. You might try to use some kind of like change of variables or something like that and make it way more complicated when in fact you could just split it apart with, you can split a numerator as long as they all have that same denominator. Moving on along. This next one, whew. All right, this one, usually if you can't use any kind of substitution, you may have to use long division. Okay, so if you have this rational function, and the usual rule of thumb is that if the degree of the top is bigger or equal to the degree of the bottom, the highest power of the top is bigger than or equal to the highest power here of the bottom, then you may have to do long division. So we're going to have to do some polynomial long division. I know that is probably not on your to-do list. It's probably not part of your favorite things to ever have to do in math, but here it goes. So to long divide the bottom into the top, we have this x squared plus 1 divided into x squared plus x plus 1. So what do I have to multiply x squared by to get x squared? Well, 1. Distribute. 1 times x squared is x squared. 1 times 1 is 1. Notice how I lined up those like terms. I didn't put plus 1 right here because that x and that 1 were not like terms. They couldn't be combined. We know with long division, we have a process. If you're dividing 3 into, do that. If I'm, say, dividing 3 into 20, I say 3 goes into 20 6 times. 6 times 3 is 18. And then my next step is to subtract. After that, if I had another number here, let me just say I had 200, then I would bring down. Same thing here. The next step here is to subtract. So I subtract by changing the bottom row of signs. That's 0. Ooh, that one just so happens to be 0. And then this x plus 0 is just x. Now, just like with normal division, once this number is smaller than this divisor, in this case, the degree is smaller than that of the divisor, you're done. Now, let me show you how we're going to write this. That was a bad example because it's a repeating one, so maybe not. Let me get a smaller number here. Let's do something super easy, like 3 into 7. So 3 divided by 7, or sorry, 3 divided into 7. So 7 divided by 3. That's the same thing as 2 1/3. That's because this is your quotient, that is your remainder, and this is your divisor. We know that when we write mixed numbers, we say 2 1/3, that really, and that this is another thing that's a little odd, but that means plus. We know normally if we smush things together, it means multiplication, but for mixed numbers specifically, it implies addition. I can do the same thing with this polynomial long division. I can take the quotient plus the remainder over the divisor. So my quotient was 1, my remainder was x, and my divisor is x squared plus 1. So here's all of that. I wanted to just kind of do it rather than just showing you it already done. I wanted you to see how it happens. How does that help us? Well, going back to our integral now, this quotient right here, this rational function, is exactly the same as this stuff. So that means my integral is the same as this integral. Now, believe it or not, this integral is nicer. I mean, definitely the integral of 1 is nicer, because that one's easy enough. Even this integral is nicer, because it can be a u substitution. So splitting these two integrals up, we get the integral of 1 dx, and then the integral of x over x squared plus 1. All right, so we're ready to make that substitution. So we'll let u be that denominator, that x squared plus 1. du is going to be 2x dx. Now remember, we have an x dx up here. We don't have that 2. So how you handle that is kind of up to you, and usually depends on who you had for Calc 1, kind of how you were taught this. But I personally look at this as just dividing both sides by 2. So I look at that as then 1/2 du is x dx. So I replace this x dx with 1/2 du. All right, so this integral right here is x. This is the one I'm substituting right now. So this is my u down here in the bottom. My derivative was 2x dx. I didn't have a 2, so I divided both of these sides by this 2 so that I can replace x dx with 1/2 du. So there's my 1/2 du. I just pulled that 1/2 out because it was just a normal coefficient. I know some people, if they have this 2x, they'll force a 2 in here by multiplying by 2 and then subsequently dividing by 2 out here. That's okay too. We'll all end up in the same place. All right, so now integrating this, we already integrated this 1 dx, and I get x. Integrating this 1 over u, I get natural log of u, of the absolute value of u, plus c. So I just went ahead and substituted back in. So I did two things at once here. I integrated and got the natural log of the absolute value of u and just went ahead and substituted back in for u. Now you'll notice that I made a little side note that you don't actually need the absolute value bars because x squared plus 1 is always positive. But I wrote them in there anyway. All right, so one more, and it's going to be pretty darn quick. If capital F of x is the integral from 0 to x of tangent t dt, find the derivative of f of x. This is using the fundamental theorem of calculus, the first part of it. And that first part is telling us that the derivative and the integrals are inverse operations of each other, right? So that first fundamental theorem of calculus tells us that if you take the derivative of this integral, you just get this stuff right here, but you get it as a function of x because you're taking that derivative of x. So what happens is you integrate this, you get a function, you evaluate it from 0 to x, and then you turn around and you differentiate it, which is going to pull it right back to where it started. But now it just has that x plugged in. So this is a result of that fundamental theorem of calculus. And sometimes these creep in on us, kind of when you're not looking. So I just wanted to do one in case you run into one and you're like, whoa, this isn't a normal substitution kind of question. It's like, yeah, it's actually a little easier. So, all right. So that concludes section 5.2.